Hello everyone, my name is Witherly Xantis and I'm joined by my team members Julia and Tyler. Today we'll be presenting recent research on the growth patterns of early mammals and their relevance to our course topics. We'll explore how understanding these early mammals enhances our knowledge of life history strategies. To start off, have you ever noticed how smaller animals like rodents often have short lifespans, while larger animals such as elephants and whales tend to live much longer? These patterns are linked to an organism's life history traits, which are characteristics such as size at birth, age at maturation, and number of offspring, which influence survival and reproduction. In nature, there's often a trade-off between life history traits, and these are reflected in two main strategies. We have R-selected species, which typically have short lifespans, small body sizes, and produce many offspring, and we have K-selected species, which tend to be larger, have longer lifespans, and produce fewer offspring. Despite these general trends, recent research reveals a surprising story about lifespans in Jurassic creatures, particularly early mammals, adding nuance to our understanding of these strategies. For example, while many small-body mammals today are R strategists with short lifespans, one early mammal studied lived for 14 years despite its small size. This research underscores the complexity of life history strategies and their variability across organisms.
Researchers from Queen Mary University of London and the University of Bonn were able to investigate the traits of early mammals using synchrotron X-ray tomography. This advanced imaging technique employs electrons accelerated nearly to the speed of light to analyze these ancient organisms. This allows imaging of a fossil without breaking and damaging the fossil altogether, unlike other imaging techniques, a very nice part of this method. With this imaging, they took a look at the root cement in the teeth of the fossils they had collected and were able to determine growth rates and when they reached sexual maturity by seeing growth rings in the root cement, similar to that of a tree. With the use of this imaging, it was observed that the thickness of the rings in the root cement correspond to growth rate and growth pattern, as shown below. This discovery was used to show the growth rates between species at 3 different time frames. The figures below show an increase in early growth rates as the time frames are later all the way up to the modern day. In these figures, we can further see the difference in the mass-specific growth rate of the 3 groups of mammals. Early Jurassic mammals have initial growth rates coming at 7 and 5 micrometer per year per gram, and showed a total change of 1 to 2 micrometers year per gram throughout the animal's life. In the Middle Jurassic, there appears to be slightly higher initial growth rates between 12 to 8, which eventually leveled off to 8 to 4, showing a change of 2 to 4 micrometers year per gram. It is worth noting that during the Middle Jurassic period, there was a very high diversity observed. However, growth patterns are generally higher and more similar to the shape of extant mammals. Lastly, extant mammals had very high initial growth rates coming in between 25 to 15 micrometer year per gram, and significantly higher total changes averaging between 10 to 15, despite there being some variability. It is also worth noting how the growth patterns in extant mammals compared to early mammals show both an increase in growth rate and a reduction in lifespan over time, and this is reflected by the increase in beginning thickness of the cementum, followed by a large dip down in the extant mammals.
Our findings reveal distinct growth patterns across the Jurassic period and modern day. In the early Jurassic, non-mammalian mammalia forms had slow linear growth throughout their lives, typical of K-selected traits. In the mid-Jurassic, growth rates were slightly higher than the early Jurassic, with juvenile growth rates being markedly higher than in the late stages of life. The former's growth pattern was shallow and sigmoidal, indicating a shift towards faster growth compared to earlier species. In the present day, growth rates have become steeper, with a more pronounced sigmoidal pattern and species having shorter lifespans, and this reflects a further shift towards faster growth and earlier maturity, indicating R selectivity. It is evident that the Jurassic period was crucial for the development of mammalian life history traits, particularly the emergence of sigmoidal growth patterns. Researchers believe the mid-Jurassic is when the live fast, die young strategy first emerged, with growth patterns resembling those of modern mammals, though less extreme. It is also worth noting this increase in growth rate was accompanied by a reduction in lifespan, reflecting a shift from K-selected to R-selected life history strategies.
This begs the question, why did these early mammals live so much longer despite their small size? Looking at their growth rates, we see that Morganocodon, who weighed 17.9 grams, had a slower growth rate compared to similar-sized extant mammals, who weighed between 20 and 30 grams. In its first year, it grew at 5.22 micrometer year per gram, which slowed to 4.42 by its final year. In contrast, Imagritus had a much higher and steady growth rate at 19.06 micrometer year per gram throughout its short life. Now, let's connect this back to the broader idea of life history trade-offs. The key trade-off in life history strategies involves the allocation of limited energy to 3 main areas: growth, reproduction, and survival. Endothermic animals like modern mammals have higher energy demands because they must maintain a stable body temperature. As a result, they tend to grow faster, reach sexual maturity sooner, and reproduce more quickly. But at a cost, they don't live so long. For Morganocodon, which had a slower metabolic rate, its energy budget was more balanced. This allowed for slower growth, longer survival, and ultimately a longer lifespan, traits typically associated with K-selection. This is a significant contrast to Imagritus, which followed the R-selection strategy: quick growth, early production, and short lifespan. To conclude, life history strategies in mammals are more complex than we often think. Rather than fitting strictly into the archaic dichotomy, many species, both past and present, fall along a spectrum, displaying a mix of RNK traits or intermediate strategies. A potential factor that we discussed that can help explain some of these deviations is metabolic rate. However, other factors like environmental conditions, energy availability, and reproductive strategies also play significant roles in shaping life history patterns. Overall, life history strategies are shaped by a complex interplay of factors, making them more nuanced than the simple archaic framework suggests.